Welcome back to my channel. We're going to be talking about Unit 6 material, starting with Riemann sums. So, before we get started, we're going to look at some things that kind of lead up to Riemann sums. So, if we know that a car is traveling at a speed of 50 miles per hour for 2 hours, then find the distance the car traveled. So, one of the things that we can do is we can take our miles per hour, how fast we were going, and multiply it by the hours. So, 50 miles over 1 hour, that is 50 miles per hour, times our 2 hours. Because we have a fraction, I'm going to also put this in a fraction. When I do this, this is going to cancel out our unit of hours. So 50 times 100, 50 times 2 is 100, so we get 100 miles. And if we were to look at this, can we represent it in a graph? So if we think about what's going on, we have our two pieces of information here, miles per hour, how fast we're going, and how long we are going for. So this is going to be hours. This is going to be mph. I'm going to make this 50 up here. We have 1 hour, 2 hours. So if we were to draw a graph of what our problem looks like, we were going 50 miles an hour for 2 hours. So we have a straight line here across, ending right at 2 hours here. Well, if I think about how we could get 100 from this, we are looking at an area. So if I'm looking at this distance right here is 50. This distance right here is 2 hours. And so everything inside of this area right here is going to give us that 100 miles. So this kind of brings us into an introduction of what the area under a curve looks like. So we have the area under a curve. We're going to be talking about that a lot in this unit. But we're going to start with just finding legitimate area of geometric shapes under a curve. We like to use rectangles just because they're kind of easy to work with. We have a base times a height to get us our answer. But we can also work with other shapes, which we'll talk about in a later section. We call these Riemann sums. So Riemann sums are when we take rectangles and divide up a graph into different rectangles to form this area under a curve. We're going to be looking at left Riemann sums, right Riemann sums, and center or midpoint Riemann sums. This tells us what we are going to use for the height of our rectangle. So we have used a left Riemann sum with one subinterval to approximate the area between the curve of VQ of t and the t-axis from 0 to 2. So we are going to be looking at this function right here. We're going to use one rectangle to do that, and that rectangle is going to be a left Riemann sum. So what we want to do is we want to kind of like draw in what we have going on here. So our interval right now is between 0 and 2. We want one interval between 0 and 2. So what we want to do is we want to look at whatever is the leftmost x value. So if I'm looking between 0 and 2, our leftmost x value when we're looking at this graph or on a number line would be 0. So 0 is going to be kind of our piece here that takes everything into account. So at 0 we have a y value of 1. So this right here is going to be our height. And more importantly, it's going to be our height for the entirety of our interval between 0 and 2. So the first rectangle we're going to be looking at is this rectangle right here. So one thing that you may notice is we are missing a lot of space here, and that's okay. We're not going to be worrying about that right now. We're not worrying about what kind of approximation we have. We're just looking at how to manually do it. So we have a left Riemann sum. So I'm going to use some notation here. They were really nice, and one of the notations we can use is an L for left Riemann sum. And because we have one subinterval, I'm going to put a 1 as a subscript. So once again, this means left Riemann sub one subinterval. And then all we're going to do is find the area. So we're going to look at the base. The distance between 0 and 2 is 2. The height, the distance between the bottom, our x-axis or t-axis, and our y value is 1. So we have our base of 2, our height of 1, which equals 2. So we're literally just taking the area of a rectangle and plopping it on a graph to estimate an area. Okay, so now that we've done that, one thing to think about. Looking at this graph, we can see there's quite a bit of missed area here under our function. So this is not a very good estimation. So let's look at another one. Use a left Riemann sum with 2 equal subintervals to approximate the area of the curve and the t-axis between 0 and 2. So now what we're doing is we're taking our graph here and we're going to be doing 2 rectangles. So when we look here, we have our interval from 0 to 2. I want 2 equally sized rectangles, so I'm going to go ahead and cut it into 2 pieces. Our cut is going to be right here at x equals 1. We are looking at left-handed Riemann sums again, so we're going to be using that leftmost number for each interval. So our first interval here is between 0 and 1, so between 0 and 1, 0 is the leftmost number, so we're going to be using that y value to help us out. That y value is 1 still, so I'm going to use this y value of 1 over that full interval from 0 to 1. This is going to be the area of 1 of my rectangles. On the other hand, if we're looking at the other one, we're looking at the interval between 1 and 2. So the leftmost point between 1 and 2 is right here. This is about 1.5, so that's what we're going to be using. And we're going to use that y value of 1.5 for the entirety of our rectangle. So we have our second rectangle. So now we're going to go ahead and use our graph and those rectangles to help us out. So L2, the left Riemann sum of 2 equal subintervals, is equal to, we have our first rectangle with a base of 1 and a height of 1. So we have 1 times 1. And we're going to add that second rectangle to get our total area, which has a base of 1 and a height of 1.5. So this first part came from that first rectangle, while the second one came from that second equally sized rectangle. We're going to multiply these out. So 1 times 1, 1 times 1.5, and add 2.5. If we look at our function, once again, there's still some space above our rectangles and below our actual function line, where we're going to notice that this isn't a very good estimation, but it's a better estimation than what we got before. So we know that our area is going to be bigger than 2 and now bigger than 2.5. Use a right Riemann sum with 2 equal subintervals to approximate the area between the curve and the t-axis between 0 and 2. So once again, we're going to do two equally spaced rectangles, which means we're going to use those same x values, 0 to 1, 1 to 2, but this time we're going to use the right Riemann sum. So let's talk about notation. We used L for left, we're going to use R for right. We want two equally sized subintervals here. Based off of what we did before, we already know the base of the first one and the base of the second one are going to be the same, which they both happen to be 1. So now all we're doing is trying to figure out what the heights are. So let's go look at what we got. So our first one here, between 0 and 1, the number that is to the right is going to be the number 1. So 1 is going to be our y value here. So we're going to use that y value of 1/2 to kind of help us out here. The one thing to notice is that this rectangle, if I use that value of 1/2, it's going to be a little bit above our graph. So this is a little bit of an overestimation at this current moment. So our y value here is 1.5. So I'm going to go ahead and put that in. So 1.5. And this is that first rectangle. Okay, our second rectangle we're going to use, we have the points 1 to 2. 2 is more to the right than 1 is, so we're going to use this y value at 2. And we're going to use that for our full interval here. Unlike the other one, this one's a little bit more of an overestimation than our first rectangle, but that's okay. So we have a base of 1 still, and we have a height of 3. So height of 3 is going to be what we plug in here for that second rectangle. We're now going to go ahead and multiply them out. We have 1.5 plus 3, which gives us 4.5. So one of the things that you notice, or you may notice, is that these are both above our graph, so this would be an overestimation. So right now what we know is that our actual area is between 2.5 and 4.5, which is actually a pretty decent range, especially for only doing 2 subintervals. So the thing that we need to know is that our estimation for that area is going to get better and better the more rectangles we add in here. So if we only have one rectangle, we would get a pretty drastic error on here because we're going to have the most amount of space that's not kind of covered. As we add more rectangles, we can see that the space is kind of closing its gap. So as I keep adding more rectangles, the amount of space that is below the graph that we don't have covered is getting smaller. So to find the exact area, what we need is we need infinitely many rectangles. And one thing to keep in mind is we're not going to ask you to draw infinitely many rectangles. That would be impossible. Also, that would just be really unfortunate to look at. So we're not going to be asking you a ridiculous amount of rectangles, but we will ask you a fair bit. I would say not to expect more than 8 on an AP test. So we can say certain things about our approximation depending on what we know about our function. Left-hand sum is an underestimation, while our right-hand sums were an overestimation in this case. So in this case, we had an underestimation, and the right-hand sum was an overestimate. But this is only true when our function is increasing. So the function we were looking at was going upwards. If we flip it to a decreasing function, our overestimate and underestimate are going to flip. So on the other hand, when our left Riemann sum is an underestimation, or an overestimation, while our right-hand sum is an underestimate, our function is decreasing. We can go ahead and look at what that might look like with a linear function. So if I have a function that looks like this, it is increasing, and I looked at two random points on here. If I did a left-hand Riemann sum, and this is the leftmost point, I can see that there is that space between my rectangle and my line. On the other hand, if this is the rightmost portion of my function, then I know that if I were to draw my rectangle, it's going to be a little bit over. So we have an overestimation. So this is our left, this is our right. If I were to flip that around, and look at a decreasing function, our leftmost function would be here. And we can see that when we use the left side to find that height, it goes a little bit over. Whereas if I use the right this time, it's going to be a little bit under.